he gave us a little warning, but the next presentation is going to be from our friends JP and John, coming from Canada and providing some experiences that they have. JP is primarily role, other than kind of supporting wind in Canada and the Northwest Territories specifically. He's a wind prospector and does a lot of work in putting up met towers, a lot of those in icing climates, so comes with a great deal of experience in that regard. And then also John has been working primarily as a consulting engineer for the last 8 or so years in the wind space, and before that worked with Yukon Energy and put in some of the very early turbines in the Whitehorse area that had a lot to deal with icing. Both of them graduated from University of Waterloo, which is kind of fun. But without further ado, they're going to give a kind of an overview of a presentation that they made a number of months ago. They're stand-ins because a couple of our original speakers, who would know that it was spring break when we held this concert? Okay, and JP, you're starting, correct?
Yes, I am.
Thank you very much, Ian. I'm very happy to be here, and it's a wonderful opportunity to always come to Alaska and learn from you guys. This presentation is a mixture of two things. One is about the monitoring and also I will provide you with a bit of a conceptual idea of how wind works, especially in these parts of the world, and also talk about monitoring and icing concerns, and then John will talk about the icing mitigation with respect to wind production. In the Yukon, there's been wind monitoring activity since the 1980s. There was a few stations installed in places that turned out to be negative and didn't show very much promise for wind. However, part of that was partly because we didn't understand it very well. In the 1990s, there was a much more serious effort, especially by Yukon Energy, to monitor the wind to understand whether there is potential. It took a geologist by the name of Douglas Craig to understand that it was actually windier on mountaintops than it was in the valleys. And he knew that because he would fly up to these mountain sites to go look for, prospect for geology, but then he realized that maybe it's windier up there after all. So that kind of spurred a new hunt, like a little gold rush for wind, and that helped Yukon Energy did start doing more monitoring on the mountaintops, and it resulted in the installation of two wind turbines. And there's been a fairly extensive wind monitoring program throughout the Yukon over the last 20 years, and it's still going on. One of the things that we didn't understand, one of the problems we had with setting up towers is sometimes we'd put them in places and realize that wasn't a very good place after all, and maybe we should have tried to understand it or to model it. And so that sort of led me to go back to university to understand how wind works, what affects wind, what makes wind flow in mountainous terrain. And some of the things I've found out, I'm showing to you now. One of the main, very important things that happen up here is there's a temperature inversion that occurs in the winter, and that affects how wind flows, especially with respect to height. And winds in the valleys are typically very different than winds on mountaintops, and I'll show you a little bit more later. The word geostrophic means air that flows way up there that's not affected by ground, but it flows because it's affected by the earth rotating. We'll talk just a little bit more about that. As a result, because we know wind is more prominent on mountaintops, we also need to be aware that there's icing issues, which we found out in Yukon. Yeah, stratification is the result of temperature profile differences between top and bottom. the air in the winter, the air tends to get colder near the bottom, and you tend to get dense air sitting at the valley bottom, and that tends to prevent any motion, any wind motion from above from pushing down into the valley. So this cold air tends to sit in the valley bottom. And just imagine when you're in a valley, and like this actually, your wind in the valley tends to just follow the valley axis, just like a river does. It's very similar to how a river flows. This is to illustrate. I was talking about the temperature inversion, and this is a winter profile. I hope that you can see this at the back. But here's a temperature profile, an average temperature profile in the winter. And this is what you refer to as the inversion. Typically, your temperature will increase all the way down to the surface, and that's what you see in the summertime. But in the wintertime, the air cools down quite a bit at the bottom in the valleys. So just imagine this is just the mountaintops beside, and we're in a valley here. And I'll just move forward a few slides just to show you where that is. Oh, that doesn't come out very well. There's a valley. This is the White Horse Valley in the Yukon, and it's a long valley, fairly deep. The surface of the valley is 700 meters above sea level, and the mountaintops are around 2,000. Uh-oh. I can't go back. Oh. Am I going forward or backward? Okay. So with the temperature inversion, the other thing that occurs is in the wintertime, there's higher winds in the winter. So here's a wind speed profile in the wintertime. And what happens here is at top, this profile here, the winds are actually across the valley. And down here, the winds are following the valley. And there's a low-level jet that occurs, a maximum wind speed that occurs within the valley as the air flows across the valley. And that is just like a river. When you think about a river, you look at where the maximum water speed is in a river. Well, it's usually right in the middle of the river and somewhere below, well, probably somewhere around near the top of the surface, just below the surface. So it's just like this. The air that flows in the valley tends to flow like a river. And that's the winter time, so you get this inversion. And then in summer, where your profile tends to be more neutral, and of course in the summer there's not as much wind, but you get more evenly distributed wind speed throughout the layer from the valley bottom to the mountaintop. And this is just to illustrate what happened, some of the ideas of stratification that goes on in mountainous terrain. So here these clouds are sitting in the valley, and this is winter time, and usually in the winter, actually, often it's warmer up on the hill. This is a site from Heckle Hill here, a view from Heckle Hill looking down in the White Horse Valley. This is on Heckle Hill, and we're looking down the White Horse Valley here. Same thing up here, it's the same valley. But you can see, and actually in the winter, it is, you can feel the wind, and it's usually a little warmer, whereas down in the valley, it's much colder, and the air doesn't move as much. It's a little more still. So why the seasonal variation? As I pointed out just a few slides ago, your summer winds are less than your winter winds. Why is that? Well, if you imagine the globe, the Earth, it has the equator, and the sun's shining on the equator. Well, the sun shines on the equator, all that heat is produced near the equator, that warm air rises, and then it goes towards the poles. And the poles are colder because they're not as warmed up by the sun. So in the winter, there's a bigger temperature difference because our pole's a little further from the sun, away from the sun, so it's colder. So there's more of that air exchange between the equator and the North Pole when it's wintertime. And so more temperature difference means higher pressure difference, and higher pressure difference means it's windier in the winter. So, however, sorry, it says here, however, the winds in the valley tend to decrease in the winter, and that's in the valley, and that's because there's no sun shining in the valleys. There's not as much sun shining in the north. So in the valley, the air just cools, and whatever cold air is produced anywhere, it just tends to go down, it drifts down into the valley because cold air is denser than warm air. So the coldest place is always at the bottom of the valley, anywhere you go. So if you want to get warm, just climb up a hill, and when it's really cold in the winter, just climb up a hill and you'll find that it gets warmer. This is an illustration of the differences between summer and winter. It so happens I pulled out a Fairbanks, Alaska file because there's weather balloon stations scattered across the world, but there's one in Fairbanks and there's one in Whitehorse, and just illustrates the difference in wind speeds from summer to winter. And here, let's say, for example, in June, the winds at the station in the bottom of the valley in Fairbanks is around 3 meters per second, whereas in the winter it drops down to below 2. Whereas up above, this is 1,500 meters above sea level. That's, don't know how many feet that is, 3 times that, 4,500 feet above sea level. Whereas the surface station is around 200 or 150 or so. So up above the mountaintops, you can see that the wind does increase during the winter time, and then it's lower in the summer. This is just an illustration of how inversion affects the wind. This is the Whitehorse Valley again. This is the orientation north, and in year round, when we have winds coming from a particular direction, in the valley you'll have winds coming from up or down the valley. It doesn't. So, but if you just look at the annual average, that's what you see. But in the summertime, when there's no inversion and there's more opportunity for air mixing into the valley, you'll see much more wind coming from the same direction as those that are from the mountaintop. These wind roses are actually at about 2,400 meters above sea level. That's from weather balloon data in the Whitehorse Valley. And what I'm trying to illustrate here is that in the wintertime, even though you have these winds coming from, say, the northwest here, in the valley itself, the winds are actually coming from the south. This is sort of an extreme example, but it shows that the valley can be completely decoupled from the winds above. That's not completely true because everything's pressure driven and it's all related, but you'd think that if your wind's coming from the northwest, then it should be pushing the air in the valley down in the same direction, but it isn't. The valley's driven by pressure, not by the wind above. So winds above mountaintops, they're typically geostrophic. That means when you're well above the surface of the Earth, the wind follows the pressure lines. And the reason they do that is because the Earth spins. And if the Earth wasn't spinning, the sun would be heating the equator, and then the air would just simply go north towards the pole, and then mix. But because the Earth is spinning, it causes the air to move due to this Coriolis effect. And the rule of thumb is when you're way up above and you're following the wind, usually your high pressure is to the right and your low pressure is to the left. And so you get these high pressure systems and low pressure systems, and the air just moves along these parallel to these pressure lines. Now that's the opposite for the Australians. It's the opposite. The high pressure is to the left instead. Just a note for you guys. And so in the valley, though, like I said earlier, the wind is still very much controlled by the valley axis. It responds to pressure, but it's controlled by valley axis. And this sort of illustrates that. This is the prevailing wind coming from the southwest in the winter, well, all year round. The average winds in the Yukon over the mountaintops come from the southwest. However, in the valley, it strictly follows that valley axis. And this is another illustration showing that when your wind comes from, this is again the geostrophic wind, the wind that are well above the mountains. High pressure to the right, low pressure to the left. Wind comes from the southwest, and so the high pressure is what drives the valley wind. When the wind comes from the northeast, high pressure is to the right, and so that high pressure is what drives that wind from the north down the valley. Now, moving on to icing issues. air in the winter time, the water that accumulates in the air, often you find that water can be in a liquid state from 0 degrees Celsius down to minus 20 degrees Celsius. So, like, just to make a point here, water can stay in a liquid form down to minus 20 degrees Celsius until it hits a hard surface, and then it crystallizes. So super cold water will solidify on a hard surface, and that's what occurs when you have instruments out in the open and wind turbines running in cold weather, and there's clouds that appear. Then those are water droplets that are actually freezing on the surface. And usually this is worse when in the fall when there's open water, and it tends to get lessened. There's less icing that occurs once the lakes are frozen in the winter, at least in our area. In the coastal regions, that would be different. There'd probably be more icing throughout the winter because the ocean provides moisture. And here's an example of, here's a cloud that's over one of our nearby mountaintops. And this would typically, there'd be icing occurring in this scenario. So it can be blue sky everywhere else, but if there's a cloud that's forming on that mountain, there's typically going to be icing. And of course, icing has devastating effects sometimes. If equipment's not robust enough, they can fall over because of the load of icing on these instruments, and the sensors get damaged often. And it becomes very difficult to measure the wind resource. And so, yeah, and vibration, you know, the ice loading on towers can be hard. And this is an example here of how much icing can occur on guy lines. So it can get, you know, quite heavy, and you know, you can see that the guy lines can get weighed down quite a bit. And that puts a lot of weight on the tower itself. And of course the sensors, they get covered up. This is just an example. This is one of a typical Environment Canada weather station, and just a little bit of icing. It's hard to tell when there's icing on the instrument. It just shows up as a lower wind speed, and that's a difficult thing to monitor, to be able to flag out when you're looking at data. But sometimes the instruments just get completely covered up. And of course damage can happen to the instruments. Anti-icing, we've looked at that a lot over the years. Some of the conclusions we've come up with is it would be nice if there was a manufacturer that could come up with you know, a sensor that can fully cover the full body of the instrument, and not just part of it, and a sensor that could provide heat that is fairly low, because often we are in remote locations, and energy efficiency is optimum, because when you're in a remote location, sometimes you might want to do some monitoring at a site where you may someday bring a power line to, but you don't have a power line there yet. So your site is remote. It needs big battery banks. It needs renewable energy equipment, and so you need to have the lowest possible heating requirement that you can on an instrument. So size of an instrument makes a big difference. And so, you know, and yeah, that's all what this is all about. And so what happens? We've tried various numbers of instruments. This one, for example, a German model. It was completely heated, and it was great. It worked really well, but it required a lot of power. This particular instrument used to be called the Handar, now Vaisala. Actually, there's a few of those in Alaska, I've noticed. But the problem we have with this one is the heating was only on where the sensor is. And so the rest of the body would get built up with ice, and the ice would bridge over where the sensors are. And these are the ultrasonic sensors, and what they do is they send signals between each little sensor, and when there's ice in the way, it screws up the reading. There's other kinds of instruments that are heated, rotating instruments, and this is NRG, and they work well. But you know, again, there's a power requirement that comes with that. So if you're grid connected, that's fine. But if you're not, then it becomes a problem. On the story of ice detection, how initially when we wanted to find out how to measure icing when it occurs, is we would use two heated sensors, and we'd have one that would be always on, and the other one would be intermittent, the other one would be off. And when the one that would be off and one would be on, and when there would be icing, the one that was off would start accumulating ice, and it would start to slow down, and that's where you would find. And so then we had controllers that would turn that on, and that would be an event. That's how we would find out whether icing was occurring. So you turn the instrument that's intermittent, turn it on, melt the ice off, turn it back off, and then wait for another icing event. That's how we would measure it. Before we got hold of these particular ice detectors made by Goodrich. And there's two models on the market. There's one that's available today, and there's one that used to be available but no longer is. And they've talked about making this available again, and we're hoping they would. And I'll show you a picture of that. These are the two models that exist. The one that we have now and the one that Goodrich is talking about making available. This particular model is a sensor that has a nozzle that operates at high frequency, and when it builds up with ice, the frequency changes, and so the instrument senses that and turns on the heater and melts the ice off the nozzle. This model here, the whole body would actually not the whole body, I think most of the top, but half of the body would heat up and melt the ice off, and it worked effectively. This model here, however, it doesn't have full body heat. It's just the nozzle that's heated. And so what would happen is this whole thing would cover up with ice and then built right over the nozzle. And so it wouldn't work anymore. It wouldn't be effective at measuring anymore. So what I had to do is, in this particular case, is add heaters to the whole body, and just to turn the heater on whenever it detected ice, and that kept the instrument working a little better. Now I've finished my part, and I'll pass it over to John.
Thanks, JP. So as Yukon Energy, we had to learn how to operate wind turbines in an environment that ice detectors showed accumulated ice 800 hours a year. So very severe rime icing. And don't kid yourself, it's not a coastal phenomenon only. It's an altitude phenomenon that we've seen in central Yukon and northern Yukon, anywhere you go. So it'll be the same in Alaska. If you're in the interior and up on a ridge, you're going to get icing. When we started in 1993, we selected Bonus wind turbine, which was the small end of the commercial range at the time. We wanted a manufacturer that had proven technology. We didn't want to reinvent wind technology. We wanted to take good existing technology and just learn how to cope with icing. So we selected Siemens. And just to put it in perspective, in 1993, there were some companies like Bonus had a prototype 450 kilowatt machine being developed. So to give you an idea of where things have come since then. And to deal with our situation, they designed the turbine to operate to minus 30 degrees centigrade, synthetic lubricants, heaters on the leading edges of the blade, which after all are the most critical part, and some heating systems and various other pieces of equipment to prevent condensation and maintain temperature, etc. And one other small thing which, well, not so small I guess, but important for us, was looking at the possibility of a tower that could be installed without a crane. And this is the Bonus wind turbine being erected, 30-meter tower. It took about 5 hours to lift it into place. The electronic control cabinets were put in the base of the tower after it was up. Not an easy machine to raise or lower just for maintenance purposes. But it meant that this turbine was assembled only with a small 40-ton local crane. So it certainly has some advantages in certain situations. Here's a photo of the leading edge heaters, the red strips that you can see. And one thing is this heat density here is relatively low. It's 1/4 of a watt per square inch. I think 400 watts per square meter. So relatively low heat density, but adequate in light rime icing conditions to not only keep the leading edge clear, but you can see quite clearly it's keeping the suction side clear and a chunk of the pressure side as well. So it's just the warmer airflow or whatever discouraged the attachment of the icing. The challenges that we faced were that the control instruments that came with the turbine had heated bearings, but that wasn't nearly enough. They suffered under severe icing, came to complete stop. The stall regulated blade has about a 4-foot tip that turns to 90 degrees, which is the air brake, and maintaining electrical contact between the main part of the blade and this rotating aerodynamic brake was unsuccessful. And ultimately, we were not able to maintain that as reliable electrical contacts, and so the blade heating in the very end of the blade had to be sacrificed. And another thing that's worth pointing out here too is that the typical control algorithm for wind turbines are that if there's a discrepancy between the power output and the measured wind speed, there's a shutdown on the basis of there's an error somewhere. And when you get icing, of course, you get depression of the wind speed. If you've got good anemometers, heated anemometers that measure the wind speed unaffected by icing, but the turbine blades are, power drops down. If the control algorithm doesn't recognize that a lower power output is quite all right when you have icing, because the alternative is to have nothing, then the turbine shuts down. So to maximize energy production under icing environments, you really need to let the turbine run as much as it can, as long as safety isn't compromised through vibration or anything like that. This is a picture of the Bonus 150 turbine, which did not operate through one serious icing event, because we also learned that overhead power lines in severe rime icing environments don't stand up. We had to go to a buried cable to get reliable feeder operation. In this case, you can see from this icing event, there's a handrail here on the catwalk for maintenance, and there's about ½ a meter or about 18 inches of ice that is built back up into the wind from the handrail. And this ball of ice here, those are the control instruments with infrared heat lamps on them trying to keep them going. And without power, they just became a ball of ice. Under severe rime icing conditions, we found that the leading edges stayed clear of ice, but you can see both the suction and the pressure side built up with ice. And so we realized that 6 inches wide heating on the leading edge was not adequate for good performance. So some of the solutions we dealt with, wider heaters. When we replaced electric heaters, we put wider heaters on the leading edge of the blade. We put a black fluorourethane coating on about 3 years after we first installed the turbine, because Bonus would void the warranty if we put it on to start with, because they were concerned about overheating of the blades in the summertime and delamination of the fiberglass. The black coating we put on in 1996, that same coating is on today 15 years later. So there was a question about longevity. Well, if it's put on right, it has a very long life. On the Bonus turbine, it's been on for 15 years. Going to fully heated instruments was certainly necessary, and Bonus was also very good. Well, I keep talking Bonus. It's Siemens now, of course. They were very good working with us to change the control algorithm of the turbine to allow it to operate at lower power levels than expected based on the wind speed, because getting some production is better than getting none. This is a picture of a startup with the black coated blades. This is the turbine had been shut down. In fact, I believe in this case we'd had a failure in one of the heaters, and so the heating system was turned off altogether, because we did get then an imbalance and a surging of the power output with only 2 of the 3 blades having heated leading edges. But you can see here that the black coating has certainly encouraged the ice to come off, and the huge buildup you get on the leading edge, particularly towards the tip, it crumbles off relatively easily. And all you need to get from leading edge or full blade heating surfaces or black coating, all you need is to loosen that surface where the ice is attaching to loosen that ice from the surface. The wind will take care of blowing it away. You don't need to melt the ice, you just need to loosen it and scrape it off, or let it fly off. And excuse me, to sort of continue on with the work, we thought that a pitch regulated machine rather than a stall regulated machine might be more beneficial in an icing environment. And we got funding for another turbine, and in 2000 we installed a Vestas V47-660, which at that time was again the low end of the commercial range. The big machines had become much bigger then. So pitch regulated, Vestas was comfortable with black blades from the start, and we doubled the size of the heaters on the leading edges. And of course, without the blade tip brakes, there was no issue with continuity for heating the entire leading edge. And at our request, we were able to get a shorter tower, so we didn't need such a tall crane to put it up. After all, this was a test site as opposed to production, so we could learn as much from a 37-meter tower turbine as a 50. And this is a picture of the 2 turbines overlooking the Whitehorse Valley. The altitude here is about 4,700 feet, 1,400 meters above sea level, and about 2,500 feet above the town. That's the Whitehorse Airport down there. So we still had some challenges. We still have icing downstream, as it were, of the heaters on the surface of the blade. Ultimately, the solution would be to heat the entire blade surface, and I'm really pleased to hear that some manufacturers will be coming forward with these options. Vestas was less willing to work with Yukon Energy at the time to change the control algorithm, and in fact they flat out refused at the time. So the turbine continued to shut down whenever the power output was down to 75% or less of what it should be, which meant that in fact the old stall regulated bonus outperformed the Vestas machine during the winter time. And ultimately, of course, for successful operations, then full surface blade heating is required with reliable ice detectors to control the blade heating. But again, my view is that you don't need enormous amounts of heat, because you don't need to melt the ice. You just need to loosen it on the surface, and relatively low heat density will do that, particularly when it's got an ice coating on, because it's not exposed to the -30 or whatever. And just to, this is an annual temperature and icing profile. The ice detector information are the blue lines at the top. The thicker the blue lines, the heavier the icing. This is annual temperature profile on Heckle Hill. And although the popular wisdom at the time was that you only get icing, from 0 to -10, the reality is we've seen rime icing down to -30, and in other locations in Yukon we've seen rime icing at temperatures down -35. So it's not limited to the warmer temperatures. And what we did to look at production losses is we developed an actual power curve, which is the red line here, and the blue line is the actual power being produced. So the production we would expect is in red, the blue is what we were getting. So during an icing event here, you can see that we lost production pretty much down to 0. The upper line indicates the icing severity, and you can see here that following the icing event, the production comes back into line, and and the blue and the red are back together, which is what normal performance is. And this is a typical graph of 10-minute actual data. This was in March 2001, I think, actual performance data and during the icing event. So quite a depression of the power curve with relatively modest icing because of the turbulent flow over the blades. So what do we need for operations in icing environments? We need blade heating that properly works, that is designed, and manufacturer supplied systems are certainly the way to go. Black surfaces certainly assist. The ice-phobic coating, well, it's kind of hard when you put it on black in the first place. It's kind of hard to be sure whether the ice-phobic nature has made a difference or the black color or some combination. But for us, it was a relatively cheap solution for the benefit, even though per liter or per gallon, it's fairly expensive material once it's put on. Most of the cost is in the labor putting it on. Rotor balance and vibration does need monitoring. We haven't seen big issues with our rime icing, and certainly with our rime icing, ice throw, which is a concern where you've got freezing rain and glaze ice, not a real concern for us, and in particular because it's a remote location. You don't have people walking underneath these turbines. So for larger power grids, ideally you'd have machines that could operate to -40 degrees and designs that minimize the crane size. Be nice to have more turbines in the 300 kilowatt to 1 megawatt range, and there are still a few around, and I'm pleased to hear that Enercon is considering installing one in northern Quebec that's 800, because it probably fits well, good combination or compromise between crane size and turbine size. And certainly be nice to have the optional blade heating for situations where it's required. Where it's not required, don't waste your money. And in small communities, again, operation to -40 and optional blade heating is nice. Getting away from cranes, which is a big part of the cost, would be nice. Maybe in time that will come too, and I think more selection and more competition is always good. And the simpler, the better. And I can't overestimate getting local people involved and also expanding the remote monitoring and maintenance capabilities, and it's become pretty much standard now, and I'm really pleased to hear the comments about that in this conference. So, thank you very much.
Any questions for, very quickly? Yeah, great.
Got battery issues. A second microphone. I can just talk about it.
Yeah, just talk about it and we'll repeat your question, please.
I had problems with those black coatings getting them out to remote communities. I was wondering if you ran into the same thing of it was considered hazard. I had to meet the hazardous waste standards, and also you said the price was in labor. I found if I tried to do that in a remote community, I didn't have the right, atmospheric or room conditions for the proper. I couldn't get the humidity down low enough to make the proper. So I found it not capable of doing it out in the remote location.
That is probably the case. It's
Repeat the question.
Oh, so the question is, let me think how to phrase that. The question was the logistics dealing with coating like Stay Clean. It's hazardous material and so needs some special treatment in terms of transport, handling, and also when you're applying it, you need a good well ventilated atmosphere, and surfaces have to be dry and clean and so on. So I would agree it can be a challenge to install in remote locations. In Whitehorse, we haven't had to worry about transport. There are enough transport options there that that wasn't an issue. I am certainly a very strong proponent of having these coatings put on by the supplier under very carefully controlled factory conditions. We had a situation where the Vestas turbine, we had to apply it ourselves on an aftermarket basis. First time we put it on, we had very wet weather. We had to have tarped enclosure, and in that case, we had some of it coming off, and the blades had to be redone in spots after 3 years. That did not happen with the bonus. That was applied in the field right on the wind turbine, but conditions were good, and it's been on for 15 years. And the Vestas has been good since that reapplication as well. So I agree, challenging conditions.
Yeah, I was trying to fly it out by playing it. It was cost prohibitive.
Yeah.
And I didn't have the right, even in summer, the right conditions to be applying it.
To be applying it, yeah.
My question is a little bit off the topic in the sense of economics and finance, not of icing. Since your turbines are the oldest compared to the Alaskan installed turbines, how is the payoff process for installations of the turbines? Is it paid off at this time? Can you say? Because we're starting to getting statistics about the cost and benefit analysis. And what is your experience about that?
When you do the analysis on a typical utility basis, levelized cost of energy, cost of capital, and all of that, installing a single wind turbine, or in this case, 2 individual wind turbines in a test locations, it is not economic. However, we recognize that in order to have wind available as one of our future generation options, we had to learn how to cope with icing, and we had to learn whether we could cope with icing so that in a future installation, a wind farm might be economic. We needed to be able to assess that. So it was a prototype, both of them really, prototypes test situation where we did not expect those individual turbines to be economic. I can tell you that in the better years of operation, we had in the order of 20% capacity factor out of the bonus. We had hoped for 23 to 25, so we didn't get there. And in terms of O&M cost, on a not including capital, just strictly annual O&M cost, we were as low as 4 cents per kilowatt hour. Other years were a bit higher, but overall, we learned a great deal. And you need that knowledge in order to make wise decisions on whether you go forward with a larger wind farm. And Yukon Energy is now considering the possibility of a 10 to 20 megawatt wind farm.
Other question?
Did you use a tilt up on the Vestas, or did you bring in a crane?
We brought in a crane. And just to give you a perspective, the installed cost was just under $2 million. The mob demob on the crane was $90,000. Just mob demob. Sorry. Mobilization and demobilization, bringing the crane in and taking it out again. And that's road access.
Other questions?
Ice throw. Any data for damages?
Any data for damages? No, we've
Yeah,
had.
I mean, is it just blue sky here? Ice.
Well, as I understand it, maybe Per can answer that. I don't think there has ever been a claim against the insurance company for damages because of ice throw.
There have been.
There have been?
Yeah, there haven't been injuries. Most of the damages are actually to equipment at the wind farm. But there have been damages almost completely in Europe.
The learnings that you had must have been shared with manufacturer. They benefited from your learnings. Did they not subsidize you? Did you get any
No, they didn't subsidize
So it's
us.
basically
No.
free research for them.
We've been very free to share that information. At least, during the time I was at Yukon Energy, we presented papers in a number of conferences and so on, and our view was that it was to our mutual benefit to share this information. We were getting the benefit of a lot of work that was being done in Finland at the time. They were working at this perhaps a year ahead of us. They started, I think, 92. So we've been open.
Let's move on at this point. What we'll plan to do, thank you too.